Ah, there's a magic button that only engineers know about. Apologies for that. Okay, well, I'm going to tell you a little bit about what we call global change, which includes climate change. But it's very important when we talk about sustainability that we obviously emphasize climate, but we don't stop there, because many other things are happening to the global environment, and they're interlinked, and they all have to be considered when we talk about sustainability. So what I'm going to try to do today is, in 3 parts, tell you about what we call the Great Acceleration in the Anthropocene. This is the outcome of this process of global change. Then I'll talk about a science-based approach that gives us some guidelines about what we do about this thing called Planetary Boundaries. You can guess what they are, but I'll describe them in more detail a little bit later. And then I'm going to turn to something I don't know much about, but I'll try to apply what I've talked about in those first 2 parts to the challenges for architects, designers, engineers, and so on, following on from what Tord said. Well, Tord spent a lot of time scaring you about heat. Now, I knew Tord was going to do this, so I thought I was going to talk about cold for a bit. This is the Australian Antarctic Territory. And Australia actually claims 42% of Antarctica. So in fact, if you include that, we're the coldest country on the planet, despite all those heat maps. But nobody lives there, of course. Now, the reason I'm going down here is not because I really want to talk about cold or Antarctica. It's because it's an important place for understanding what's happening to the planet. This is from the Australian Antarctic Territory. We go down there, take aircraft to the middle. We do something like this. It's sort of hard to see, but this guy's got a very big drill, and he's drilling down into that ice. And we use some mechanized drills that can go down even further. And they pull out cores of this ice. I don't know whether you can see that very well. If we turn those lights down, or if there's some shades that come down over the windows, that might help a bit. Oh, there we go. Maybe that's a little better. On that right hand, you see this core of ice that's coming out of this big drill bit. And so what we can do is we can actually slice that up really thinly and analyze each little layer of ice. And bits of fossil air are trapped in there, as well as different isotopes of oxygen and hydrogen that make up water, make up ice. And from that, we can actually tell what the Earth was doing year by year, all the way back in time. And that's what one of these graphs looks like. That's from one of those Antarctic ice cores. There are 3 wiggly lines. I'm only going to focus on the red one in the middle for the moment. That's a proxy for temperature. So that's 400,000 years on the bottom, not 400 years, 400,000 years. And you can see that we as a species, Homo sapiens, evolved somewhere between 2 to 250,000 years ago. This is important because notice the temperature range that we've evolved into. This gets on to what Tord's talking about. Our bodies are not equipped to cope with temperature that goes beyond that range. And you'll see in a moment that's exactly what's happening. So the Earth operates in nice cycles, most of the time in ice ages. So in fact, most of the time we're in a colder environment than we have been in the last 10,000 years. But that last 10,000 years has been unusually long for these warm periods. And that's been important for us because it's allowed us to develop agriculture, villages, and cities. It's called the Holocene, an epoch in Earth history, only about 10,000 or so years. If we go to an ice core from up here, or near here, in Greenland, and look at only the last 100,000 years of that record, you can see how erratic the climate was in the North Atlantic region. Lots of spiky events, temperature shooting up and then dropping back down. But basically it was an ice age. Until, again, about the last 10,000 years. And notice how unusually stable that was. So we can track human development on there. Humans only got out of Africa about 85,000 years ago. And the first wave of them went down across the bottom of the Arabian Sea. Remember, in the Ice Age, sea level was 100 meters lower. So a lot of things were connected that aren't connected today. So it allowed people to get out of the Horn of Africa, around the bottom of the Arabian Peninsula, across into South Asia, going along what are now the continental shelves below the sea around India. But at that time, they were fertile lands. And so as they went, they dropped off populations who stayed and developed there. But the last pushed that the first group of migrants who got out of Africa, they arrived in my country, Australia, about 65,000 years ago. And they're the present-day Australian Aborigines, by far the longest living culture on the planet. But those of us who have European background, like the Australian settlers and obviously people who live up here, we come from one of two migrations from South Asia. So our relatives come from present-day India. About one migration about 55,000 years ago. Those are the Mediterranean peoples. Northern Europeans about 33,000 years ago. But the point being is all the way through this, we were only hunter-gatherers everywhere. Until we got into this, what you might call a planetary sweet spot, the Holocene. It was warmer, it was wetter, we learned how to grow crops, we got excess food, we could develop more complex societies, we specialized labor, developed villages, cities, and so on, leading to civilizations in the last 3,000 to 4,000 or 5,000 years, and of course leading up to the contemporary globalized civilization we have today. So the Holocene, we think, is actually a fairly special epoch in Earth history. But something's happening to this epoch now. All these images are from Australia, and they're all within the last 5 years. And in every one of them is evidence that we're destabilizing the Holocene. We have floods, we have bushfires, we have dust storms, we have intense heat. This is heat in the mid-40s in the temperate zone of Australia, that's Melbourne. So hot that it was buckling rail lines. We're bleaching the Great Barrier Reef. Tropical cyclones are getting more intense. And it's not just happening in Australia, it's happening elsewhere. So this is why I'm talking now about global changes. We're seeing these tremendous changes in climate. But we've also vastly modified the nitrogen cycle. That's pre-industrial nitrogen, global cycle, post-industrial. Huge new big arrow coming down. That's industrial fixation by the Haber-Bosch process. Putting massive amounts, double the amount of reactive nitrogen is now going into the system, affecting waterways, drinking water, lakes, rivers, and so on. Those red dots that fall on top of one another, that's where large dams are around the world. So every major river, except a few in Siberia and Canada, is now dammed. It does not flow naturally to the sea. Humans are now co-opting about 40% of the surface water on planet Earth to use for our own purposes, greatly affecting freshwater ecosystems. That's land that's given over to cultivation, or most of the large percentage of that land in those areas is cultivated. Now we have to do this to grow food for 7 billion people, but it's vastly changed terrestrial ecosystems. Now all of these things have happened without any climate change, and already they're putting enormous stresses on ecosystems and on some human populations around the world. Then on top of that, of course, we put the fact that we're destabilizing the climate. This is a tropical cyclone coming into the Queensland coast in Australia. It was absolutely massive. It's a third the size of the entire continent. We hadn't seen one that big before. This was in 2010, Cyclone Yasi, 2011 actually. And similar ones now have hit the Philippines in the last couple of years and so on. And of course this is what Tord's talking about. This is the surface temperature change on the planet from 1901 to 2012. It's heating up. But as you put more energy in, all sorts of other things are happening to the climate system in terms of storms, water cycle, and so on. But that's coming on top of all the other changes. And this is what we talk about when we talk about global change. So I was involved in a big international program studying planet Earth from a global change perspective. It happened to be headquartered in Stockholm. So I was up in Sweden for about 7 years, back from 98 to 2005. As part of that project, though, we wanted to look at all those snapshots I just showed you and systematize it and say, let's get some real indicators for the globe and see what is happening to planet Earth. So we said, well, we know that these changes are driven by humans. And we have a pretty good idea that the Industrial Revolution might have something to do with it. So let's go back and look at what's happened to what we call a human enterprise. That's the totality of human activity. Our numbers, our activities, and for the purposes of this talk, our technologies are really important. And let's try to get some indicators. And you can see what we used: population, real GDP for economy. These are all globally added up. I'll get onto the equity issue a bit later. But these are all globally added up. Foreign direct investment, urban population, and Tord mentioned that. Primary energy uses, resource use, fertilizers, waters, dams, paper. And then how we connect, transport, telecommunications, tourism, and so on. So you see these curves sweeping up. But what really amazed us when we did this, we started the year 1750 because we wanted to capture the Industrial Revolution. It actually wasn't the Industrial Revolution that was the big factor. It's what we call the Great Acceleration, 1950, post-World War II. And as a natural scientist, I was a bit stunned by this until I met a good colleague named John McNeill, who's written a 20th century history of humanity. And his title is really revealing. It's called Something New Under the Sun. And he talks about the institutional, the governance, the economic, those dimensions of what was changed after World War II. The final shattering of the old European institutions that predated the Second World War. And out of that chaos came entirely new institutions, the International Monetary Fund, the World Bank, neoliberal economic principles, which gained a grip in the Western world and eventually after 1990 everywhere. So these greased the wheels of the technology which was already coming online from the Industrial Revolution, but greatly accelerated by the war effort. And so we hit a tipping point in terms of human connectivity, technology, knowledge, institutions, that just, in a complex systems point of view, allowed us to explode. And we did. And you can see all these indicators of this explosive development of humankind. And then, of course, being natural scientists and studying global change, we wanted to say, what's happened to the Earth? Or as we call it, the Earth system, the single system that Tord showed in that last slide, that blue ball out there in space, is a single system. And so we said we need indicators for that too. We did the same thing from 1750 now to 2010. We've updated these just this year. You see the three famous greenhouse gases up there, CO2, methane, nitrous oxide. Stratospheric ozone. Surface temperature is actually the only direct measure of the climate system. Ocean acidification, of course, is related to CO2, but it's somewhat independent in that it's a chemical phenomenon in the water. The bottom six of these are direct impacts on ecosystems, on how they function, on their structure. Coastal zone, marine systems, tropical forests, and the terrestrial biosphere as a whole. Notice that in these graphs, they're all also sweeping up. Many of them again around 1950. And all of them are now being pushed outside of that nice 10,000 year period that we've developed our own civilizations in. So this is probably the strongest single collection of evidence that we're not in the Holocene epoch anymore. And it's not just climate. Climate's very important, but so is the biosphere in its own right. We tried to visualize this, or I should say National Geographic did in 2011, this great acceleration. Well, in fact, they almost missed it. This is an interesting story, because they wanted to talk about the development of humanity and so on. And they used this little equation that impact equals some aggregate of population times affluence times technology. Look at the technology coming in. If you don't think design and engineering is important, have a look at that. It's right up there with the economy as a whole and with the population, numbers of people. So what they did was they had three axes, those three. They had population going up on the left there at the base, technology going out on the right. They had trouble finding an indicator. So basically they just used the number of patent applications as some indicator of how technology is developing. Maybe you can help us find a better one. And then affluence, world GDP, because consumption of stuff correlates really well with affluence. The wealthier you are, the more you consume. Pretty good relationship. So they made this chart, and you see a little tiny square, a rectangle down at the bottom. That's 1900. That's the entire human enterprise in 1900, that little bit. And then they had 2011, which is this huge box at the top filled with fridges and airplanes and cars and all the stuff we consume. And so I was an advisor to that article in National Geographic, and they were very happy with this map. They sent it to me and said, you should be really pleased with this. I said, not at all pleased. They said, what's the problem? I said, you've missed the whole story. I said, what do you mean? I said, you didn't put it in 1950. And they argued, and they said, well, it's going to be halfway up. Why should we put it in? I said, put it in and you'll see why. And so at my insistence, you see the next little box down at the bottom is 1950. There you see the great acceleration. So you go half a century from one little box to the next little box, and a bit more than the next half a century, and it explodes. So visually, this is what we're talking about. This is what John McNeill is saying when he says, this is something new under the sun. And this is really, in my view, when the world started moving out of the Holocene was 1950. There was a real breakpoint in the human enterprise. So, the Anthropocene. The word was first used in the year 2000 by Paul Crutzen, who was a member of this program based in Sweden at that time. He's also known, he's won a Nobel laureate, he's a chemist, atmospheric chemist. And he's won his Nobel Prize for working out the chemistry of the ozone hole. So he understands the Earth system pretty well. But we were at a meeting and we were discussing the past changes in the Earth. And we had a lot of really good scientists who looked back 100 years, 300 years, a couple thousand years. And they were talking about the Holocene all the time, which is, of course, the term the geologists use. And Paul was getting really irritated. And he jumped up and he said, stop using the Holocene, we're not in the Holocene anymore. And then he stammered around and looked for a word and he just blurted out Anthropocene. And of course now it's stuck. It's being used by lots of people. And the geologists might even come on board too. But to understand what we're talking about, let's talk a little bit about Earth as a single complex system with its own indicators and characteristics. And I'm going to go back to this ice core. You've seen it before, but now I'll analyze a little bit more carefully. A good analogy, by the way, as a single system is a human body. It's very complex. We have heart, lungs, limbs, brain, nerves, and so on. And of course, medicine specializes in those different things. You go to different specialists. But we're one system, one single system. And so is the Earth. In fact, it's not unlike a human heartbeat. I'll talk a bit about blood pressure too there in a moment. Anyway, excuse me. The Earth exists in two states, basically, at least in the past 1 million or 2 years. One of the states down here at the bottom of the Ice Age, you can see they're a bit erratic and they're long, nearly 100,000 years long. And then these spikes, these are warm periods. And the interesting thing is, they are driven by the changes in the Earth's orbit around the sun. Well, I shouldn't use driven, they're triggered by it. Just like you have a pacemaker. But the real work gets done internally in the Earth system. It's CO2 moving between ocean and atmosphere. It's ice growing and retreating and reflecting more or less sunlight. We understand how it works, somewhat like we understand how human body works. But notice the regularity. If you're healthy, your heartbeat is regular. It's not erratic. If it becomes erratic, your doctor gets worried. So look how regular that is. 100,000 year cycles. That goes back 1 million years. By the way, before that, it was about 40,000 year cycles, but that's another story. Those are the interglacial warm states that we know very well. But now I want to do something else, talk about a thing called limit cycles. It's a bit like blood pressure. You've got 2 levels of blood pressure. And if it's normal, there's a certain range you stay within. And if your doctor sees you going too low or too high, she gets really worried. Same thing with planet Earth. I'll show you what these limit cycles are. There's one for the blue line. The blue line is actually carbon dioxide. By the way, notice how closely carbon dioxide and temperature are in sync all the way through. And this goes back millions of years. When the CO2 is really high, 1,000 ppm, the world was ice-free. So there's a big, strong correlation there. But notice how CO2 drops to almost the same level in every ice age and rises to about the same level, just like your blood pressure. That's called a limit cycle, very characteristic of any complex system. There's the limit cycle for methane, and of course temperature also has a limit cycle. Temperature always rises to about the same amount. Now I'm going to put on what's happening now. That blue line is where CO2 is now. It's drawn to scale. Okay? So we've blown that limit cycle, big time. There's methane. You can hardly see it. It's just on that scale on the right. But you see the green arrow going up. It's worse than CO2, by the way, in terms of increasing it. Now, interestingly, what's going to happen to temperature? Well, that's where temperature is going. Here's a 2,000-year record of temperature over the Earth's land surface. And you see there's been a very, very, very slow cooling trend. Bit of ups and downs, and that has to do with solar variability. But you see the spike that's colored in red. The spike in red is actually the measurements by instruments. These others are proxies, you know, the pollen, the tree rings, things like that. So you can see the natural variability of Earth, and you see the spike at the end, which is what we expect, because we've changed the energy balance by changing those greenhouse gases. This is an interesting bit of work that just came out in the year 2015, a couple of months ago. And this is that same graph I just showed you. You see the black line wiggling. But notice those blue lines banding it. That is the limit of how sun can affect climate. So that's back calculated from the orbital changes around the Earth's orbit around the sun. And the wiggles within that are generally solar flares, 11-year sunspot cycles, that sort of solar variability. But notice how the black line has just shot up. That's because we've blown the Earth's limit cycles. That's because we put so much CO2 and methane in that it's overwhelming what the sun does to the planet. So this is another piece of evidence that we've left the Holocene. The Holocene is between the blue lines. That's the Holocene climate. And now we're shooting up quite rapidly. Now this is only a little under 1 degree in average temperature. You saw what Tord showed you in terms of the projections for the future. Do you know how much hotter it was when the dinosaurs were around? And CO2 was between 1,000 and 2,000 ppm. It's about 5 degrees on average. Of course, it was much hotter with the extremes. And another thing that fits exactly what Tord is saying about large areas being uninhabitable for large mammals, there were no large mammals back then. Thermally, it was a bad place for us to be. We can't get rid of heat fast enough. Great for reptiles, not so good for large mammals. So this is, in an Earth system point of view, it's exactly what Tord's talking about in terms of a planet that's going to be really rough to live on. Okay, I'll do very quickly what he did. Those are the temperature projections. I'm stopping at 2100. He went out beyond that. RCP 2.6, that's if we really get our act together, get emissions under control. Most people think it's impossible. Well, we can hope for miracles, I guess. If you're living in Australia right now, it doesn't look too promising. The red one is the business as usual, just keep burning CO2. Now those look like nice smooth curves. You know, and you show that to a policy person, they don't get too excited. They say, well, a little bit of increment, we'll adapt. Okay. But now what I want to do is put it in an Earth system frame. That's that graph I showed you, 2,000 years, with a temperature spike where we are today. Now I'll put those projections on the same time frame. Remember, this is 2,000 here, so 2,100 is there. Okay. So let's put those, compress those graphs to 2,100. That's what it looks like. So think about that from an Earth system point of view, or if you're a medical doctor from a blood pressure point of view or whatever. It's a huge spike in an extremely short period of time. So it's not just the magnitude of this temperature change, it's the incredible rate at which it's occurring. It sort of makes you think twice about whether adaptation is even possible. So there's where we are now. This is what most scientists think we're committed to, for two reasons. One is, most of the heat's going into the ocean, huge thermal mass, and it hasn't equilibrated with the air yet. Even if we could stabilize emissions tomorrow and then start bringing them down, we're headed for another at least half a degree or maybe more, simply because of the inertia in the ocean. But of course, we can't get emissions to zero very soon because the economy takes a while to transform, so that'll probably push it at least to 2 degrees. But business as usual takes us up between 4 and 5. And that really is a collapse scenario because it's hard for us to, as scientists, to imagine any society that's going to be able to cope with that magnitude change that fast. So that's really what we're talking about. Now, from a point of view of a complex system scientist, you saw those curves that Tord showed going up at various levels depending on the emissions. Well, complex system scientists say that's actually not what's going to happen. So it's not how complex systems actually work. They work like this. There are tipping points in them, highly discontinuous processes. We know what some of them are on the Earth. For example, loss of the Greenland ice sheet, shutdown of the North Atlantic circulation, loss of the Amazon forest. A lot of them are connected. Now, for us as humans, they don't seem like tipping points because it's going to take a bit of time. But from the point of view of the Earth system, when we're talking about hundreds of thousands of years, they can be fast. So, the idea is that somewhere there's a tipping point for the planet as a whole. And the best guess that scientists have now is below 2 degrees we're pretty safe. We're not safe from a lot of individual impacts. But we probably are not going to see a major tipping point. We'll see a few, perhaps Greenland will go, but we're not going to see Antarctic go, for example. However, most scientists say that if you go much above 4 degrees, you very certainly trip all sorts of tipping points, and in fact probably push the Earth to eventually to an ice-free state. We know it's very stable as an ice-free planet. So this is really, I think, what the question is can we stabilize the climate before we trip too many of these tipping points and push the Earth as a system into another state? Gaia would be quite happy. Earth has been in an ice-free state for millions of years, but it's not at all good for large mammals. So that's the point. All this we're talking about stabilizing the climate, we're not trying to save planet Earth. Planet Earth has been a snowball, and it's been ice-free. And life, in some forms, has continued. After extinction events, it's re-radiated, it's evolved again, and so on. And given enough time, it'll do it too. And there's no way, no matter what we do to it, we're going to break Gaia completely. So what we're talking about now is really about our benefit as a large mammal on a planet that could get much hotter. So this is the question really we're facing. Will the Anthropocene be a short spike? We get it act under control and we return to Holocene-like conditions? Or are we probably not even going to go into an epoch, but an entirely new age that's going to last for millions of years? And the answer is we don't know. And that's making it difficult for geologists to deal with this thing called the Anthropocene. Okay, that's the problem. What do we do about this? And this is the second part of my talk. And I'll talk a little bit now about planetary boundaries. This idea actually came out of Sweden, out of Johan Rockström's lab up in Stockholm, the Stockholm Resilience Center in 2009. When he got together a group of about 30 scientists, I was one of them, but people from all around the world to say, how do we handle this? And so we started from the scientific perspective I just showed you. The Earth is a complex system, as a single system. States and transitions, stable states, tipping points, a state you just don't want to go into as a human being. So the idea is we made a judgment saying everything from our past tells us that the Holocene state's really good for humans. We do better in the Holocene than we do in ice ages. But the assumption is going rapidly outside of the Holocene is going to present real problems, maybe even existential problems for humans. So then it becomes a scientific question. Where are the boundaries of the Holocene state? What do we need to do to keep this state stable? And so that's where the origin of the planetary boundaries concept was. A lot of people misinterpret it. It does not try to prescribe what humans should do. It only prescribes the boundaries of the playing field, to use a sporting analogy. We can be as creative as we want. We're not saying anything about population, although larger populations have less maneuverability within the safe operating space. And we're not prescribing anything about technology. Technology is really important because it's one of the most important tools for maneuvering within the safe operating space. So this analysis is science-based, and it's based on the characteristics of planet Earth. I use an analogy sometime that a lot of my humanities colleagues don't like, but I use it anyway as a scientist. And that's to say, if we were a bunch of Martians or whatever coming in and viewing this planet like Tord showed, this nice blue, really interesting living planet out there, and saying, let's do some experiments with it. And you're sitting out there in the spaceships and they're ripping out some of the biosphere and they're pouring in CO2 and they're acidifying the ocean and saying, how far do we push it before this thing flips? This will be fun. And this is what we're trying to do as planetary boundaries. How far can we push this thing before it flips? But of course now the pushing is happening from the inside, from those species as part of the Earth system. So we came up with what we thought were the minimum set of parameters we could use to classify or describe the state of the system. So climate change is definitely one of them. You see there are 8 others around there. And of course they're interlinked. Atmospheric aerosols are related to climate. Chemical pollution is related to rate of biodiversity loss, and so on. So we set about describing how far can we push each of these parameters. That was the original paper. It was published in Nature in 2009, longer version in Ecology and Society. It created a firestorm in the scientific literature, a lot of criticism. People didn't like to be told that actually there might even be planetary limits. This Earth is not like, well, if you read Australian children's books, it's not like a magic pudding. All right? We've got a little story about this big magic pudding that you keep slicing it and eating it, it keeps regrowing. And you can eat as much as you want, you still have your magic pudding. And Tony McMichael, who's The late Tony McMichael, a colleague of Towards and mine, used to talk about this a lot. He said, we think the Earth's a magic pudding. Well, it's not. So where are the boundaries to the pudding that we actually have? So we did an update, which we published a couple of months ago in Science, updating a lot of the fundamental science behind it. But we came up with basically the same answers. So some of the processes actually do have tipping points. That's on the left, where you push a parameter and nothing happens and you think you're safe, hit a tipping point and it flips. You know this probably from basic chemistry if you've done science, a lot of tipping points there. Others simply change slowly, but they erode the resilience. They erode the ability of the Earth to take shocks and deal with them. So we color-coded this. You see sort of a sliding scale of green on the left, which we think is safe. This is what we call a safe operating space. Then you go through a zone where you got really increasing risk. And then you got the zone on the right where you're pretty certain you're going to flip something or get into really nasty space. And this is the real dangerous territory. So it's like a traffic light. Green you go through, yellow if there's a big truck coming the other way, it's pretty dangerous territory. And if it's red, you're going to get killed if you go through a busy intersection. So it's a good analogy. So this is what these color coding looks like. This is the acidity of the ocean. Okay? Look at 280 ppm. That was before the Industrial Revolution. Safe everywhere. Okay? Marine organisms were well suited to that level of acidity. All right, 380, look at the poles. You're starting getting to the yellow zone there. Here's where we are today, 400. The yellow zone's expanding. There's even a couple of yellow zones around Australia in the tropics. Now, what's the evidence that some of these are in trouble? If you look at some of the calcifying organisms in the polar seas, you now find they have deformed shells. They're not growing as well, and so on. If you look at the Great Barrier Reef and you see a yellow zone up there, that's off the Queensland coast of Australia, you find that calcification rates have dropped by 15%. So the whole system hasn't fallen over. But now we're saying is you've actually transgressed the boundary in those areas and you're in dangerous zone. And then, of course, if you go on and keep emitting CO2, you start to see red creeping in. That means you're really going to trash ecosystems. There's not much doubt about it. And again, because CO2 is more soluble in cold water, these things start at the poles and creep toward the equator. All right, some politicians are saying, well, we're at 400. Maybe if we're lucky, we'll stabilize at 500. Look at 500. Oceans are going to be unrecognizable in terms of marine life. But look at along the east coast of Australia. Great Barrier Reef, largest living organism on planet Earth, completely gone, trashed. This is what we're talking about. These are big changes in the system. Okay, we'll look at some other boundaries. This is land system change. It's hard to see the outlines of the continents. They've sort of disappeared. But basically, it's the major forest areas, the tropical, temperate, and the boreal are the big forests here in northern Sweden, across Siberia, across Canada. Amazon is still okay, just, we think. But Africa's in trouble. Southeast Asia is really gone. And you can see it in terms of biodiversity loss, all sorts of local pollution problems. Most of the boreal forests are in the yellow zone now. That we see problems, fires are increasing, insect pests are increasing, and so on. They haven't fallen apart yet, but they're on the way. So this is how this traffic light works. Again, here it's hard to see. This is nitrogen. This is where we put nitrogen on the planet. And we've exceeded the boundary for this, but notice that it's in 4 major areas: Central United States, Western Europe, the Indo-Gangetic Plain in India and Pakistan, and Northern China. Far too much nitrogen is going on. And not surprisingly, that's phosphorus. Pattern looks the same for the same reason. We're throwing a lot of that on to grow food, which is important. But in many areas, we're throwing far too much on. Now, the interesting thing is, when you look at much of the rest of the world, it's green. And particularly in Africa, they can't afford this stuff. So in fact, they're struggling to grow enough food. Whereas in Western Europe, Middle America, and these 2 big Asian countries, we're putting far too much on. So there's an equity issue here. There's a distributional issue to some of these boundaries. So we tried to put these together, and you can see the traffic lights starting at the center of this little concentric diagram being safe. So when you're green there, you're still in the safe zone. But if you look at P and N, we're way outside. We've even gone beyond the yellow zone. Same with biodiversity loss. Extinction rate is between 100 and 1,000 times background rate. We think we shouldn't be any more than 10, and then we should aspire to get that close to the background rate. Way outside that. Climate change raises eyebrows because people think it should be red. Okay? What's our boundary? The safe zone is 350 parts per million because all the scientific evidence we can gather says that if you stay below 350, you're extremely unlikely to cause a lot of problems that you can't cope with. We're about 400, so we're halfway to where we think the outer limit is, which is about 450. 450 corresponds to a temperature rise of 2 degrees or a bit less. So it's close to the 2-degree guardrail. So we're already seeing a lot of impacts halfway through that zone. That's what the yellow zone means. That we're in dangerous territory, and if we hit the red zone, we're going to be in really deep trouble. So that's how you use the planetary boundaries approach. And I want to emphasize here this thing in the middle. This framework does not dictate how society should develop. It simply dictates what space of the Earth system they shouldn't go into. So that gets over to you guys. I'm going to start talking about design and engineering in a moment. Because how we engineer, how we live, what we do, what we produce, what we consume, is one of the biggest levers we have in dealing with the planetary boundary framework, whether we stay in or go across. And so I think that's going to be the critical thing. So, where are we going in the 21st century? A bright future of continued growth, as many economists would have us believe? Or are we sailing towards a global collapse? Many societies have collapsed in the past when they become dysfunctional given outside stresses. I'm going to close now. I'm not an expert in design and engineering, but I just want to talk a little bit about what I think some of the lessons for design and engineering might be when you take this global sustainability long-term with a long view. So, first thing I'll say, in the back of your mind, you should keep this in mind. The human impacts on Earth are approaching or exceeding in magnitude some of the great forces of nature. This only occurred since the 1950s. It's a completely new situation for human beings. Second, these operate on much faster timescales than the rates of natural variability. So things are changing greatly in magnitude, and it's fast, really fast. And taken together, they've produced what we call a no-analog state in the dynamics and functioning of the Earth system. Simple engineering problem. 2 airports in Australia. Sydney Airport, Brisbane Airport. Both low-lying, right on the seacoast. One airport, Sydney, did not believe us, and we said, hey guys, you're in a no-analog state. They went back and looked at the historic 1 in a 100-year flood, built a new runway based on that. We told them they were idiots. They were bad investors. The bean counters, the economists came in and said, oh, you stupid scientists, it's far too costly to raise the runway. 20 years ago they did that. Right now that runway is inoperable a growing number of days a year. Why? You get a good wind and the waves are coming over the end of the runway from Botany Bay. They hadn't calculated the fact that sea level had already risen 20 centimeters. Doesn't sound like much to a bean counter, but it's very big to a scientist. Brisbane Airport, very different story. They got the scientists in, and the scientists and engineers went to the economists, and the economists actually had to listen to their investors, who were us, superannuation funds. And we put a bit of pressure on them saying, hey, listen, this isn't an environmental issue, it's our investment. This is an investment issue. We don't want you screwing up like Sydney did. And they didn't. They built that runway 3 meters higher. They're going to handle a 1 in a 100-year flood that's predicted for a meter of sea level rise. Okay? Cost them hundreds of millions of dollars more to build that runway higher. But they did the sums and said, in the projected lifetime of Brisbane Airport, that's actually a smart decision. So engineers have to realize you're in a no-analog state. You can't just look at the past rules of thumb and design for the future. Toward mentioned cities. Again, you can't see the map behind this. There is a map of the world. 1950, start of the Great Acceleration. Top 10 megacities. Biggest one's Tokyo. Oh, sorry, biggest one's New York, number 1. 12 million. You can see where they are. Europe, North America, Buenos Aires, 4 of them in Asia. 1950. It's 2010. They're the top 10. Look at the size and look where they're shifting. Guess what? Tokyo's now overtaken New York by a long shot. But look at this. Shanghai, Dhaka, Delhi, Karachi, Mumbai, Calcutta. Biggest cities in the world now, overtaking the Europeans. In fact, none of the European cities is any longer in the top 10. What's the projection for 2025? Tokyo's still number 1, but just. Others are creeping up on. Delhi, nearly 30 million. Dhaka, 20 million. Mumbai, 26 million. And so on. This is how fast this is happening. Again, something that engineers have to take into account, and urban designers. This is a hell of a lot of people. All right? You know how big the Australian continent is? Tokyo is 50% bigger than we are in population. One city. So these are orders of magnitude we haven't thought about before. Show you what it looks like. You can see this is a photograph taken in the Shenzhen area of China, 1982. I was a scientist in CSIRO in 1982 in Canberra, sort of well into my career. That's rural, okay? 1982. Same picture from the same position. Notice that ridge in the middle going from the left over here to the right to that bit of water. Let's just fast forward about 30 years. There it is. Same place. There's that ridge, that little black spot. That's Shenzhen. That's how fast China is building. Not just urban areas, but megacities. Think of the design and engineering challenges you've got with that. And you've got a changing environment, rapidly changing environment on top of it. So what are some of the challenges? There are three big ones that are often talked about in terms of greenhouse gas emissions. Obviously, energy systems have to be changed. Transport is really important. That's turning out to be tougher, by the way, than changing energy. And of course, built infrastructure. So those are the three big ticket items that we need to deal with. But if we look at this from an Earth system perspective, rather than a sectoral perspective, as you design for transport, as you design for urban areas, for energy, for buildings, this is what needs to happen. We need to stabilize the energy balance at the Earth's surface. It has to do mainly with the gases we put in the atmosphere, but also to do with reflectivity and pollution, aerosols. We need to halt the erosion of what we call biosphere integrity, the functioning and structure of the living world. This is a living planet, completely unique, and we're totally dependent on the biosphere to regulate this place. And yet we're ripping out species at 100 times at least the background rate. And we need to reconnect with it. How do you reconnect people in those megacities? To me, that's one of the ultimate design questions that we face. Well, at the same time, you've got the more immediate things that you design for, enhancing urban amenity, livability, improving quality of life. So these things have to come together now. So let's look at energy. Well, solar is really taking off. Solar photovoltaics, despite hostility of our government, rooftop solar is being taken up at an increasing rate. We now have between 15 and 20% of Australian homes have solar PV. It's shaking up our energy system. Solar thermal's been around for a while. We need to start moving into bigger systems too. Storage technologies are changing. So this is really on the go. Built infrastructure. This is a building I was actually involved with a little bit in the design. This is the Fenner School of Environment and Society at the ANU. And I was director of the school. We got the money to get that going. We aimed for what's called a 5 green star. That's our measuring system in Australia. In fact, we achieved a 6 green star, and the challenge to the building company, the designers, the engineers was, you got to deliver it on time, you can't go over budget, and you got to do a better job. It was a fantastic learning experience. They were angry at us at the beginning saying, we can't do this. And we actually sat down and spent a lot of time as scientists saying, yes, we can, let's do it together. And now the head of that company goes out and talks about how great it is that we can build these good buildings on, within budget. So there's learnings that can be had by collaboration. Here's an example from China, where they're generating their own electricity in this huge building with solar panels everywhere. And it's interesting architecturally. And look, you can hardly see there's a lot of green at the bottom too. Again, innovative design can help solve these problems. So we need to account, obviously, for emission reductions or renewable energy generation. Some cities now, some buildings in Melbourne, for example, want to be not only carbon neutral, they want to be carbon positive, they want to be taking up carbon as the building operates. Electrifying ground transport. You guys in Europe are way ahead of us. This is an Australia example. We're only now thinking about a corridor there where we can use high-speed rail instead of flying airplanes all the time between our major cities of Melbourne, Canberra, Sydney, and Brisbane. And that hasn't gotten off the ground yet, but hopefully we'll get there. What has happened is a renaissance in urban transport. And it's basically rail-based, it's electrified, and in places like Canberra and Adelaide, where we're generating now large fractions of our electricity by renewable, it's reducing emissions from transport sector, as well as delivering what it's supposed to, which is relief of congestion, more livable cities, development along the corridors rather than sprawling and so on. But you got, on top of that, you got to design for the fact that these things have to be carbon neutral. There's a great story in Canberra. We're putting a light rail system in. The first segment of it will be operational in 2020, so construction starts next year. By 2020, Canberra will be 90% renewable, a combination of wind and solar. So I did the calculations. If you move from a car there into that light rail, your emissions drop by 97%, close to decarbonization. Right? Canberra's not a big city, we're 500,000, but yet we're doing that in 5 or 6 years. That's because you can roll out renewable really fast. So again, it's not only the design, it's bringing these things together, integrating electricity with transport. Connecting people to nature. Do any of you guys recognize that place? It's Dubai, United Arab Emirates. Building, not quite as fast as the Chinese, but they're building pretty fast. You know, it's already a dry place, but it's pretty hard to find any vegetation there. I wouldn't want to live in a place like that at all, no matter how well it was air conditioned. I spend my time in a place like this. That's actually not a city at all, it's Northern Australia, Arnhem Land. The only place where you can find Australian Aborigines who still live at least partly in a hunter-gatherer tradition. Great place to go. Immerse yourself with nature. Not too much, there are big crocodiles there that come straight through from the Cretaceous. Anyway, so the idea is we need to reconnect people with the natural world. There's a lot of research now that it's crucial for our mental and physical health. That if you remove people from nature, we become dysfunctional. We become dysfunctional socially, and we have trouble individually in terms of our health. So it's important in design that we actually make these connections all the way through. Here's an example of how we might do this. Active transport. Here you see the light rail line, but alongside it, bicycle path, lots of trees and so on. Community gardens. Swedes are pretty good at this, and there are a lot of them around Stockholm, I know. English-speaking world isn't so good yet, but we've got to become better at that. Building green infrastructure that's more efficient, but has trees around it, has water around it. Here's some other things. There's rooftop gardens, green walls. The wall is a living wall. And people are finding that the workers, employees in there actually perform better and are healthier when you have green around you. Green precincts, not just designing a whole part of a city that's green. This is my home. It's hard to see, but the whole city is embedded in the bush. If you fly over Canberra, you'll only see a little bit that looks like a city. Most of it will be trees. People, the first comment they make to me is, you say there are 500,000 people. Where are they? You won't find them. But we have great connectivity with nature. Of course, we can't forget Amenity. That's a new town hall in London. Hard to see. That's, again, the center of Canberra as the station for the light rail goes in. So it's this idea of connecting people, getting emissions down, efficiencies, and so on. I'm going to close with what I call the joker in the pack. Because I've been talking a lot about the environment at various scales, particularly the planetary scale, the Earth system, planetary boundaries, great acceleration. I skated over this issue. It's a huge one. Inequality in income, wealth, and opportunity is the biggest human issue of the 21st century. Now, I know very little about how design and engineering are going to tackle this, but I just have a gut feeling that there's some really innovative things that can be done there, too, to deal with that challenge. So I'll show you, just to closing, what I think is some of the most striking data I've seen. It's becoming front and center in a lot of Western countries. This is from the United States, from one of their big magazines. You see over the last decade, there's been a lot of talk about social problems in one of the world's wealthiest countries. This, to me, is the most striking set of data, probably outside of the Vostok ice core, that ice core data that I've seen in a long time. It's two epidemiologists from the UK, Richard Wilkinson and Kate Pickett. What they did was very simple. They looked at income inequality, the gap between the wealthiest 10% and the poorest 10%. And they only took countries that on aggregate are wealthy. So they took poverty out of the equation. They didn't put in Bangladesh or the African countries. And they ranked them from high inequality to low inequality. Then they took a basket of social problems that afflict wealthy countries. You can read what they are: obesity, imprisonment, teenage births, drug addiction, that sort of thing, alcohol addiction. And lo and behold, they got an incredibly strong correlation. Cut right across cultures. Look at the best countries are Japan, Sweden, Finland, and Norway. And you say, well, 3 of them are Nordic. They probably share some cultural characteristics. The Japanese are completely different. And then the English-speaking world, well, we don't come out very well at all. And the worst one, of course, is the United States. It's so bad it's actually off the top there. It's worse than it ought to be. And I'm not sure, I haven't seen a good explanation why that's so. But the point is that the more unequal you become, the worse your social outcomes are. They have a very provocative hypothesis, hasn't been proven, it's a hypothesis. They actually say it has nothing to do with culture or engineering or anything. It has to do with the genetic code. That we've lived in small groups, we're still sort of wired as hunter-gatherers, and we live in groups of 200 to 300 and then split off. But within those groups there's a level of hierarchy. So we do tolerate differences. But you have to have a society, you can't all be equal. But once the gap between access to resources and influence becomes too high, it becomes socially dysfunctional. And that's what they're saying is happening here. And there's no way around it. You just got to solve the equity issues. So I think this is central to smart urban design. We try to do it in Canberra. It doesn't work too well, and that is we don't put public housing all in a clump. We scatter it out amongst people of different incomes and social groups. In fact, in the apartment block that we live in, we've got several apartments that are owned by the city and are rented out to low-income people. Has its problems, sometimes, but it's an attempt to try to break down this division. 2 books come out in the last year and a half, extremely provocative. Before you accuse me of favoring communism or anything, I've got to explain this. First one is Thomas Piketty, a French economist. I normally don't read economics books. I think they're too boring. But actually, this was a page-turner. I couldn't put it down. This is a fantastic book. It's data-based. It isn't based on belief systems. It's based on data going back 200 or 300 years. And the countries he uses are France, Britain, Sweden, and Germany for the long term. And shorter term, he has data for the United States. And then for really short term, he has Australia and a few others. But it's amazing that the natural tendency of capitalism is toward high levels of inequality. He doesn't say abandon capitalism, he says regulate it. He says if you want to have good social outcomes and good economic outcomes, you want to optimize it, you can't just deregulate and let capitalism go. Its innate characteristic is to drive inequality. And then you have Naomi Klein coming along, and this book, This Changes Everything, where she says the innate drive of capitalism is to drive climate change. And she uses fossil fuel companies. The capitalist system, you have to keep growing to be viable. And to keep growing, you've got to find more fossil fuels. That's why they're talking about going into the Arctic. That's why you have coal seam gas, tar sands in Canada. She said that's not just evil people. The people aren't evil. They're just living in a capitalist system that forces them to do that. So again, she says, you can't abandon capitalism. It does a lot of good things, but it has to be regulated. So this is going to be, I think, a big point of discussion over the next decade or so. So I'm going to close there. Talked a lot about the Anthropocene. Certainly don't have the answers. I know that you people in engineering, design, and architecture are going to be critically important to help deal with this problem. So as we sit here in 2015, and I think about when my daughter's going to be my age, I have no idea what on earth she's going to be living on. I think that's still open. Where on earth are we going? So let me stop there. Maybe we have time for a bit of questions. We'll certainly get some questions in the panel discussion. So thank you so much for your attention for this rather long.